8.5 kind of takes us in a little bit of a different direction. We're going to be dealing with something called variation functions, which is basically like proportions. So you guys definitely did proportions in Algebra 1, maybe even before that. So that's the stuff we're going to be working with. So 3 different types of variation. I'm going to define the first one. It's direct variation. Direct variation is a relationship expressed in this form. So a relationship that can be expressed in the form y equals k times x. So basically what that means is as one of them goes up, the other goes up. Okay, so that's a big idea. All right, so big important idea of direct variation is as x increases, y increases. Or you could say the opposite. As x decreases, y decreases. So think of something like the number of hours you work versus the amount of money you get. The more hours you work, the more money you get. The fewer hours you work, the less money you get. All right, so, and then this thing right here, the k, is something called the constant of variation. Okay, so this is the first type of relationship we're going to look at, a direct relationship, which like I said means as one variable does something, the other variable does the same thing. One goes up, the other goes up, or one goes down, the other goes down. So here's the relationship that we've got. Going with this relationship, let's say we have our first y value compared to our first x value, and say we've got a second relationship where we compare our second y value to our second x value. Okay, what we're going to do is we want to know about that value k, that constant of proportionality or that constant of variation. And so what we do is we get k by itself. So here what we do is divide both sides by x1. So when we divide this side, looks like this, and then this side we divide both sides by x2 to get the k by itself. So we'd have the left side divided by x2, and then over here we just have k by itself. So what we've just created is 2 functions that are both equal to k. So if k equals this and k equals this, then these 2 things must be equal to each other. So what we come up with is this relationship, that y1 divided by x1 must be equal to y2 divided by x2. Okay, so this is the relationship that we use for direct variation. And we're going to show you an example with example number 1 here. So if we say r varies directly as t, that opening sentence is what tells us that we're going to use this right here. Just because I have x and y right here doesn't mean I need x and y in every formula. This uses r and t, which is totally fine. So whichever one typically, whichever one they list as r, like they say r varies directly, that means that's the y. So this r would be like the y1, so this r would be like the y2, and then this would be like the x1 and the x2. All right, so we're going to fill all that in. So we would have negative 20, that goes in right here, and then divided by 4. So this one divided by this one is equal to, and then we don't know the next one, r divided by negative 6. Okay, then it becomes just like a little proportionality thing. All right, so do you guys remember cross multiplying? Hopefully. So we multiply these 2 together. We have negative 20 times negative 6. That gives us positive 120 equals, and then we multiply these 2 together. R times 4 is 4r. And so then to get the r by itself, we're just going to divide both sides by 4. Could plug that in if you want, but hopefully you know that that gives you 30. All right, so that's one example there, and we're looking at direct variation. Another very similar idea, still kind of in this category, is something called joint variation. Joint variation is really similar, except there are 2 variables that it's working with. Okay, so a relationship where one quantity varies directly, as the product of two or more quantities. Okay, so it varies directly as the product of two or more quantities. So basically, one variable is affected by two other variables. Picture, hopefully you guys remember the area of a triangle. Like area equals 1/2 base times height. Not only is the area affected by the base, it's also affected by the height. So the area is in a direct relationship with two variables, the base and the height. So that's a really good example of that. So we're going to set up the formula for this. So y varies directly as x and z. We'll throw in a third variable there. So we start with this relationship. So it's basically like this, just like the previous page, but then we're multiplying by another variable as well. Okay, so we've got that set of values, and then we have a second set of values, basically just like what we were doing on the front, okay, except we're tossing in another variable. And so basically the same thing happens. We're trying to get the k by itself, just like we were on the front. So here we divide by the x and the z. So we get this, we divide by the x1 and the z1 to get the k by itself. And then over here, we divide both sides by these two things as well to get the k by itself. So the y2 is already there, and then we're dividing both sides by the x2, z2, and we get k by itself. So the only difference is I've got another variable down there because I am directly varying with two different variables. So we combine these up, exact same logic as we had on the previous page. If these are both equal to k, that means they must be equal to each other. So basically, here's the setup we're looking at. The y is like our main variable, so when you say r varies jointly, that means r is the main variable, and then whatever it's varying with, those two go in the denominator. Okay, so that's how we're going to set this up. Find r. Okay, so read this. R is what's varying jointly, so we're going to put that in the numerator when v is 2 and t is 8. So we're going to multiply 2 times 8, so it looks just like this formula right here. If, so we set it equal to the other proportion, r is 70, so 70 is the main variable, and it's varying directly with v as 10 and t as 4. So we set that up. So we basically just plugged these all in here, except r went in for y, and then v and t went in for x and z. So simplify this a little bit. We have r over 2 times 8, which is 16, equals 70 over 40. Okay, we're going to cross multiply again, so multiply here, r times 40 gives us 40r, and then equals 16 times 70, probably a calculator problem, I'm going to check that myself. 16 times 70 is 1120. Okay, so semi-big number here. Divide both sides by 40 and we figure out what r is, so you can definitely do that in the calculator as well, and we get 28. So r equals 28 would be your answer for that one with the joint variation. Okay? So this is basically, I mean, picture it like a formula, almost like an area. So it might say, find the area when this is the base and this is the height, if you know that this is the area when this is the base and this is the height. And I know those numbers won't work out for that specific example, but it's kind of like that idea. Okay, then we have inverse variation. Inverse variation is the opposite of what we were doing on the front. On the front we said as x goes up, y goes up. Inverse variation is the opposite. It's the inverse. As x goes up, y goes down. Or vice versa. As x goes down, y goes up. So that's this relationship. So inverse relationship or variation is a relationship. And that's, we keep using that word relationship. We mean some sort of relationship between two different variables. So it's a relationship where one quantity increases while the other decreases. And I actually do want to give you guys an example of this. The example I want to give you is speed versus time. Okay, as one increases, the other decreases. So if I increase my speed, it'll take me less time to get somewhere or less time to, finish a run or whatever it is you're doing. If you decrease your speed, it will take more time to get there. So this is an inverse relationship. As one goes up, the other goes down, which is the opposite of the relationships we were doing on the front. So another proportion that we can set up here. This particular equation, say you were trying to find your speed. Speed is equal to distance divided by time, like miles per hour or something like that. So what happens with these is you've got a variable in the denominator, but this will be like just a normal number. Like say you were trying to go, 5 miles, you do 5 divided by t. Or if you're driving, maybe you're driving 200 miles, you do 200 divided by t to figure out what your speed is. So our proportion this time looks like this. We have just a number in the numerator, but our second variable is actually down in the denominator, just like this is. And we can set up a second relationship, just like on the front page, with a second set of values. And what we do here to get k by itself is we actually multiply both sides by x1. So to get this out of the denominator, we're going to multiply both sides. So I get y1 times x1 is equal to k. And here, same thing, I'm going to multiply both sides by the x2. And I get y2 times x2 is equal to k. All right. So now, since these are both equal to each other, since they're both equal to k, we know they're equal to each other. So my final relationship is I can set this equal to this. Okay? So that is my equation that I'm going to be using for the inverse stuff. So let's look at a sample of this. So x varies inversely as y. That means x is the main variable here. So x is 24 when y is 4, so you can plug them in here. So x is 24 when y is 4. So since it's an inverse relationship, you're multiplying them together in this formula, equals find x, so we don't know what that is, when y is 12. So I'm basically just plugging things into this formula right here. And then I divide both sides by 12. Okay, these will cancel, and then I get x equals, so I can actually reduce these down. 24 and 12 will reduce down to 2 over 1. Then I have 2 times 4, which is 8. So that's that answer. Okay, we're going to look at a quick story problem here. Little unusual, but this is the apparent length of an object, meaning like from your viewpoint, how long does it look? It's inversely proportional to one's distance from the object. Okay, so let's try to figure out a relationship there. So that means it's going to be this relationship. Earth is about 93 million miles from the sun. So here's what we've got. The apparent length and then the distance. Okay? So if we're trying to do like the length of the Earth, so that's what we're going to write. L for length and then E for the Earth. 93 million miles. The second variable is the distance. So here is our relationship. So it says the apparent length is inversely proportional to the distance from the object. So we're setting up this relationship right here. Length is y, distance is x. So here's what we've got. The length of the Earth times the distance of the Earth, and then length of Jupiter times the distance of Jupiter. Now we're going to plug in what we know. So Earth is about 93 million miles from the sun. So that's the distance. And then equals Jupiter is about 483 million miles from the sun. Okay, then it says how many times as large the diameter of the sun would appear on Earth as on Jupiter. So we're trying to relay this value back to this value. So to get it by itself, we're going to divide both sides by 93. So this equals, and then if I plug this in, I'm going to plug in the 483.6 divided by 93, and I get 5.2, but I still have this variable right here. So that means Earth, the diameter of the sun would appear 5 times, or 5.2 times longer than it would on Jupiter. So we would say 5.2 times as large. So to answer that last question, how many times as large would it appear on Earth as on Jupiter? It would appear 5.2 times as large, just setting up that proportion. Okay, last thing we're going to look at is combined variation. It's exactly as it sounds. It's a combination of direct and inverse variation. okay? Okay, so we get a little bit of everything. So first set, y1 equals, so let's say it varies directly as x. That means the x gets multiplied by k, and inversely with z, that means we divide z. So that's that relationship. And then we can set up an almost identical second set of data. So directly with x, inversely with z. So here we've got a couple weird things going on. What we're basically going to do to get this k by itself is actually multiply by the reciprocal of this. So we're going to multiply by z1 over x1, aka we're going to multiply by the z and divide by the x. So we have y. We're going to multiply by the z and divide by the x to get the k by itself. And then same thing over here. We've got the y over here on the left. We're going to multiply by the z and then divide by the x to get the k by itself. Okay, so one last formula for the day. Same exact logic. Since these are both equal to k, they must be equal to each other. So now this will definitely start to get confusing, so let's make a quick note. So z, this was the one that was varying inversely. Okay, and then x was the one that was varying directly. Very, very important to keep those two things straight. Okay, so whatever's up here with the y is the one that was varying inversely. Whatever is down here with the, I guess by itself, is what's varying directly. So it seems a little counterintuitive. All right, so suppose that p varies directly as r and varies inversely as t. So the t would go up here and the r would go down here. So that's the relationship we're going to be setting up. So let's plug these values in. So here's the first set of data. So we don't know t. We know p is -5. We don't know t. We know that r is 10. So we're plugging these three values into this equation right here. And we set it equal to the next set of data. So we know that p is 4 times t is 20, and then divided by r, which is 2. Okay, so let's simplify this up. First of all, 5 and 10 can reduce. Reduces down to -t over 2 equals, and then 4 times 20 is 80. 80 divided by 2 is 40. Okay, so let's multiply both sides by a 2. Let's actually multiply both sides by a -2 so we can clear out this negative as well. Okay, so these cancel and the negative cancels, and we get t equals -80. All right, and that is your final answer, and that is our last problem.